Hi, welcome to Math 1400, Nunez Community College. Today's lesson is lesson 2.2. It's verifying trigonomic identities. With verifying identities, it's different than the last section we had, which was simplifying. In verifying, we're actually trying to get the identity to look like the right-hand side of the equation. So if I have verified that cotangent of theta times the tangent of theta equals 1. We want to look at this, and I'm going to try to use one of the identities to simplify in order to know that we need to get to the answer, which is 1. With this, in order to be 1, we're going to have to be able to cancel things out. So I'm going to turn both of these to the quotient identity, and you turn them to sines and cosines. Cotangent would be cosine theta over sine of theta, and tangent would be sine of theta over cosine of theta. And we know that they must equal 1. So here, since we're multiplying the fractions, we can cancel the numerator and the denominator since they're the same. And the same thing here with the cosines, we can cancel the numerator and the denominator since they're the same, giving us 1 on the left, and it's equal to 1, which is on the right. This is going to be verifying that cotangent times tangent equals 1. Suppose we have, for example number 2, tangent of theta times cotangent of theta. Tangent of theta times cotangent of theta over sine of theta equals cosecant of theta. Sine of theta equals cosecant of theta. In this one here, we look at it and kind of do the same thing. I know that my answer is going to have to be cosecant of theta. Just by looking at it, I don't see what to do on any of the identities, so I'm going to turn this tangent and the cotangent into sines and cosines. So again, I'm going to have sine of theta over cosine of theta, because that's tangent, times cosine of theta over sine of theta, because that's cotangent, and it's all over sine of theta. Well, again, cosines would cancel out, and that's equal to cosecant of theta. Again, the cotangents would cancel out, the sines would cancel out, leaving me with, on the top or in the numerator, 1 over the sine of theta. And if we look at the reciprocal identities, we would see that 1 over sine theta is indeed equal to cosecant of theta. So then we have cosecant of theta equals cosecant of theta. Again, if in doubt, change things to sines and cosines and go from there. Example number 3, we're going to have 4 cosine squared of theta minus 4 sine of theta. Sorry, it's 4 sine squared of theta equals 8 cosine squared of theta minus 4. In this one here, we look at it and we say, I know that my answer is going to have the function cosine. It doesn't have sine anywhere in it. The right side doesn't have sine anywhere in it. So we're going to try to take this sine and we're going to try to make it a cosine so that we have only cosines, which is what we're looking for. So this says sine squared, so I need to be able to find a way to make sine squared a cosine. I come down to my Pythagorean identities since this says sine squared, and let me see if I can rearrange this. I have what? Sine squared plus cosine squared equals 1. That's my identity. And I want to get it to be cosine, so I'll bring the cosine to the other side, And this gives me what? Sine squared equals 1 minus cosine squared. Cosine to the other side. So 1 minus cosine squared can be inserted for sine squared into our identity, giving me 4 cosine squared theta minus 4 times, instead of sine, we're going to put in 1 minus cosine squared theta. Okay, now we have to distribute our -4 to both in the binomial, giving me 4 cosine squared theta minus 4 plus, because negative times negative, 4 cosine squared theta. Now, it's a matter of just combining our like terms, giving me 4 plus 4 is 8 cosine squared theta minus 4. Which is what we're looking for on the other side, 8 cosine squared theta minus 4. They are indeed equal to each other. So if you're given something that is squared, like we have here, we're going to go automatically to the Pythagorean identities and try to look at Pythagorean identities first, okay? Again, it's a matter of the more that you do, the more that they're going to be become, I guess, easier for you. It's almost like doing a puzzle where you have to be able to figure out the next move in order to put the puzzle together. The next example, which is example number 4, is 1 over sine minus 1 over cosecant. 1 over sine of theta minus 1 over cosecant of theta is equal to cosecant theta minus sine theta. Is equal to cosecant theta minus sine theta. Okay, this one here we look at, and we know where we got to go. But when we look at this one, I see a subtraction of 2 fractions. Both of these are fractions, and we're subtracting it. So, in order to add or subtract fractions, we have to find a common denominator. And the common denominator here is going to be sine, because I see sine, and cosecant, because there's a cosecant. So my common denominator becomes both things, because that's what we have. So I multiply the common denominator, which is sine times cosecant, and sine times cosecant to both. I'll put it like that since there's 2 terms. We know that this has to be our denominator, and we're seeing what we're missing. Well, this one has a sine already, so I don't need a sine. However, it does not have a cosecant, so I need a cosecant. So this is cosecant times 1, which is cosecant theta. Minus this one on the right has a cosecant already, so I don't need a cosecant. What I need is the sine of theta. And that's all over, since we're adding and subtracting fractions, it's all over the whole denominator, which is sine theta times cosecant theta. So now what we have here is cosecant theta minus sine theta over sine theta times cosecant can be written using the reciprocal identities as 1 over sine theta. So this would be sine over 1 times 1 over sine. When multiplying fractions, we can cancel out the top and the bottom, or the numerator and the denominator, leaving me with what I'm looking for, which is just cosecant theta minus sine theta. Again, showing that the identity is verified. Okay, suppose we have a next example, number 5, which is 6 cotangent squared. 6 cotangent squared theta times secant squared theta minus 1 equals 6. Equals 6. Same on this side. With this one here, I know that if the answer or the right side is 6, then I know that everything else has got to cancel out. So with this one, I'm looking at squared, and I'm looking at a binomial squared, so I'm automatically going to Pythagorean identities, and secant squared minus 1 would be in this one. So we have 1 plus tangent squared equals secant squared. So secant squared minus 1, I would bring the 1 to that side, and tangent squared equals secant squared minus 1. So we know that this is equal to tangent squared. So this will leave me with 6 cotangent squared theta times tangent squared theta equals 6. So at this point, we're going to take them and turn them into sines and cosines, giving me 6 times cosine squared theta over sine squared theta, because that's cotangent, times sine squared theta over cosine squared theta, because that's tangent, and that equals 6. And then we'll come back to everything's multiplied together. We can cancel if it's the same in the numerator and the denominator. Same thing here, giving me 6 equals 6. 6 equals 6. Okay, and the next example we're going to have, which is going to be example number 6. Yes, example number 6. We will be looking at tangent squared over secant, tangent squared over secant, so tangent squared theta over secant theta equals sine theta times tangent of theta. So in this one here, we are going to look at it and turn it into sines and cosines, giving me sine squared theta over cosine squared theta for tangent over secant, which is 1 over cosine theta. And this is known as a complex fraction. It's a fraction over another fraction. When you have a fraction over another fraction, we either multiply by common denominators or take the bottom fraction, flip it, and multiply. So we'll do that so we can see it better with canceling out. So this gives me sine squared theta over cosine squared theta, the top, times cosine theta over 1. So we take the bottom fraction, flip it, and write a multiplication symbol. Now what do we have? Well, multiplying, I got 1 on the top, 2 on the bottom, so I can cancel one of them in the denominator. And this leaves me with what? Sine theta times sine theta, that's sine squared, over cosine theta. And sine over cosine is tangent, leaving me with sine theta times tangent of theta, which is what we're looking for. Okay, verify the next identity where we have 7 over tangent theta, 7 over tangent theta plus 7 times tangent of theta equals 7 secant squared over tangent. 7 times secant squared theta over tangent of theta. Okay. For this here, I think that we should probably look at it and rewrite it as pulling a 7 out. First, before we pull a 7 out, we're going to rewrite it as looking at this being a fraction, fraction added together, and we're going to get a common denominator, and our common denominator is going to be what? Tangent. And here we already have a tangent, so I don't need it, so that gives me 7 plus, here we don't have a tangent, so that's going to be 7 times tangent squared theta, multiplying together, all over the same denominator, which is tangent of theta. Once we do that, we have a 7 in common with both of them. So now I can pull the 7 out. Once I did that, giving me 7 times 1 plus tangent squared theta over tangent of theta. So we found our common denominator, put everything over the common denominator, factored out the 7, giving me this. Now I have this binomial, it's squared. Can I possibly rewrite this as a Pythagorean identity? And if I look at it, yes, 1 plus tangent squared theta is secant squared theta, giving me 7 times secant squared theta over tangent of theta. And that is where we're trying to go, so that would complete our identity, proving our identity. And finally, example number 8 says that we have 3 secant theta minus 3 cosine theta. 3 secant theta minus 3 cosine theta equals 3 sine theta times tangent theta equals 3 sine theta times tangent theta. All right, let me erase this part so that it doesn't confuse us when we're looking at the other problem. And by looking at this, well, probably we can factor out a 3. So that probably is what we should do first, factor out a 3, leaving me with secant theta minus cosine theta. Okay, at this point, let's change them to sines and cosines. So that gives me 3 times, secant is what? 1 over cosine theta minus cosine theta. We can put it over 1 if you want to make it look like a fraction. And now we have subtraction of the 2 fractions, common denominator. Common denominator would be cosine. So I would make sure that both of them have cosine. This one already has cosine, so it stays the same as 1 minus, this one does not have a cosine, so cosine times cosine is cosine squared theta. Now we are going to look at this and look at the identity that we have. Oh, sorry. This is right. But what did I forget? I forgot to put it over the common denominator, which is cosine theta. That makes a little more sense. So now we look at the Pythagorean identity, which we have over here. If I brought the cosine to the other side, sine squared plus cosine squared equals 1. Bring the cosine to the other side, and we have that sine squared equals 1 minus cosine squared. 1 minus cosine squared. The word's not quite dry yet. So I can replace this with sine squared, giving me 3 times sine squared over cosine which then I can what? I can break this into 3 times sine theta over cosine theta. Take these two, put them together, and that would be what? 3 times sine theta times tangent of theta. Again, with the identities, at least you know where you're trying to end up. And if you know where you're trying to end up, you can kind of look as you're going along and see which identities you need to be able to fit in order to complete the puzzle. This was section 2.2, which is verifying trig identities, and I will catch you at the next.